All right, diving in today, folks, we're looking at something pretty crucial in the world of LLMs, those large language models that seem to be everywhere these days. It's all about how we can make them even smarter, more efficient, getting the most bang for our buck in terms of their thinking power.
And that thinking power comes down to compute, right? The tokens these models generate as they work through a problem.
Exactly. It's like their mental energy, but in the digital realm. So today we're focusing on optimizing this test time compute, how to make those tokens count, make sure they're not just spinning their wheels.
And this is where things get interesting because traditional training methods haven't really focused on this aspect as much, especially when it comes to feedback, right? Often it's just about whether the final answer is right or wrong, kind of like a pass-fail system.
Like a student slaving away on this massive exam, and only at the very end they find out, whoops, failed. No clue where they went wrong along the way, just that the end result wasn't good enough.
Exactly. And LLMs train like this, well, they can end up with these insanely long, rambling chains of thought, even for simple problems. And for the really tough ones, giving them more thinking time, more tokens, doesn't guarantee a right answer.
So basically, they might not be learning how to think strategically, just thinking more, not thinking better.
Right, and that's where this new research on meta-reinforcement fine-tuning, or MRT, comes in. It's really a shift in perspective. Instead of just the final answer, MRT focuses on rewarding the progress the model makes during its reasoning process. So it's like, hey, good job on that step, even if you didn't nail the whole thing yet.
Meta reinforcement fine tuning, that sounds pretty different from the usual approach. And you mentioned it's inspired by meta reinforcement learning, which, if I remember correctly, is all about models learning how to learn. Not just learning facts, but learning how to approach the learning process itself.
Spot on. So the model isn't just figuring out answers, it's figuring out how to best figure things out as it goes along. And today we're going deep, getting into the nitty-gritty of the academic side of MRT, its theoretical framework, why it's causing a stir in the field. So how about we unpack this a bit? How did the researchers frame this, making test time compute more efficient within this meta-RL framework? Well, the key innovation is how they conceptualize the problem itself. They treated each new problem the LLM encounters, during testing, as a totally fresh, independent task. And then instead of seeing all the generated tokens as just one long stream, they broke it down into these episodes.
Episodes. So not like episodes of our show, but more like chapters in the LLM's thought process.
Exactly. Think of it like distinct steps in a proof, or attempts at writing a line of code, meaningful chunks of reasoning.
So it's like zooming in on the LLM's thought process, breaking it down into these manageable bits. Gives us a finer view, I guess.
Precisely. And once you have these episodes, the goal for the LLM changes. It's not just about spitting out the right answer. It's about learning a strategy, like a meta-level strategy, for using its token budget across these episodes for each specific problem.
So it's like knowing when to try different things, when to stick with what seems to be working.
Exactly. The classic exploration-exploitation dilemma, but happening inside the LLM's mind as it tackles a problem.
This is already getting pretty deep. We're talking about the model learning how to strategically solve problems within its computational limits. This has got to be fascinating for our listeners who are really into understanding the nuts and bolts of how AI works, right?
Oh, absolutely. And to measure how well an LLM is doing at this strategic thinking, the researchers used a metric called cumulative regret. It might sound a bit jargony, but the idea is actually pretty intuitive.
Okay, let's break down this cumulative regret thing. What's that all about?
Okay, imagine the perfect student, right? The one who aces every problem and knows the most efficient way to solve everything. Think of that as our oracle.
The gold standard, the ultimate brainiac.
Right. So cumulative regret for an LLM is basically a measure of how much its performance differs from this perfect oracle as it generates its tokens, its episodes.
So it's like measuring how much the LLM deviates from that ideal, super efficient path to the solution.
Exactly. And if you're into visuals, figure 1B in the paper shows this nicely. Imagine a graph. One axis is the thinking budget. How many tokens? The other axis is the likelihood of getting the right answer. Now, our perfect oracle, it shoots straight up to 100% accuracy with very few tokens.
Efficient and effective.
Right. The LLM's path, well, it's more gradual, more meandering, and the cumulative regret is the area between those two paths, the oracle's perfect line and the LLM's actual journey. Smaller area means more efficient reasoning.
So the less regret, the more the LLM is making meaningful progress with each token, not wasting time on dead ends. This seems like a big deal for anyone who wants to see AI become truly efficient in its thinking, right?
Absolutely. Minimizing regret, it means the LLM is taking more productive steps in its reasoning process. And that brings us to the heart of this work, the method itself, meta-reinforcement fine-tuning.
All right, time to get into nuts and bolts. What makes MRT tick? How does it actually minimize this cumulative regret?
Well, the core principle of MRT is that it directly aims to optimize, or at least get as close as possible to optimizing the minimization of this cumulative regret. It's not just about the final answer like traditional reinforcement learning, which is often just, did you get it right? Yes or no?
So it's more nuanced than just a right or wrong reward at the very end.
Right. MRT rewards progress at each step of the reasoning.
So the feedback is happening constantly throughout the thinking process, not just at the finish line.
Exactly. And the big innovation is this thing called the progress reward. It's given after each episode, that chunk of reasoning we talked about, and the size of the reward depends on how much that episode increased the model's confidence in getting to the right final answer. It's all laid out formally in definition 6.1 in the paper.
So after the LLM generates a bit of thinking, MRT is basically saying, hey, did this get you closer to the right answer? If so, here's a little pat on the back proportional to how much closer you got.
Exactly. And that encourages the model to explore the problem in a smarter way. It's not just randomly trying things until it stumbles on the solution, it's learning to focus on the paths that show actual progress.
Makes sense. So there's like guiding model towards a more strategic way of thinking. This sounds really promising for complex reasoning tasks, but I'm curious, how did the researchers actually test this MRT approach? What did their experiments look like?
They ran experiments in two main settings to see how MRT performed with different styles of reasoning. First one was called open-ended parameterization.
Open-ended. So what's the defining feature of that setup?
They trained LLMs to use special markers, think and think, to kind of signal when they were starting and ending a specific reasoning step. A bit like DeepSeek R1 does, adding a little transparency to the thought process.
So the model's saying, okay, I'm thinking about this now, does its thing, then says, all right, moving on.
Exactly. And each chunk of text within those markers, that's a reasoning episode.
Got it. So in this open-ended setting, how did they actually apply the MRT, the progress reward idea?
They combined it with two existing learning methods, STAR, which stands for self-taught reasoner, and then just standard reinforcement learning using the GRPO algorithm. For STAR, they focused on keeping only the reasoning traces that both got the right answer and showed good progress according to their metric. And for the RL with GRPO, they added the progress reward on top of the usual correct and correct feedback.
Clever. So rewarding not just the outcome, but the journey as well. What about the LLMs themselves? Which ones did they use for these open-ended experiments?
Mostly models around the 1.5 billion parameter size, DeepScale R-1.5B preview, DeepSeek R1 Distill Corn 1.5B, and they did try a slightly larger one, 7 billion parameters, the DeepSeek R1 Distill Creme 7B.
Focusing on smaller models for research makes sense, easier to manage. And what about the second experimental setting? You mentioned there were two.
Ah, yes, that one was quite different. It was all about training models to do something called backtracking search. They used the Llama 3.1 architecture for this.
Backtracking, okay, that sounds like a more deliberate, step-by-step kind of problem solving.
You got it. In this setup, the models went through these phases. First, try to generate a solution, then try to spot any errors in what they came up with, and finally backtrack to a specific point in their reasoning and try to fix things based on those errors. Each of these phases, the attempt, error detection, and backtracking, that's an episode.
So it's a much more structured process, kind of like trial and error, but with built-in steps for recognizing and correcting mistakes. I like it. And how did MRT fit into this backtracking world?
Pretty similar to the open-ended setting, they used both STAR and standard RL to fine-tune these backtracking models, with the progress reward encouraging those backtracking steps that actually improve the chances of finding the right solution. Though they did have to pre-train these Llama 3.1 models first with some supervised fine-tuning just to give them the basic backtracking skills. Figures 14 and 15 in the paper show how they did this initial warm-up phase and what the training looked like.
Makes sense. Got to give them the basics before you can refine their strategic thinking with MRT. So after all these experiments in both open-ended and backtracking, what were the big takeaways? Did MRT prove itself?
This is where it gets exciting. The results were pretty compelling. First off, significant performance boosts, and I mean across the board on all these tough mathematical reasoning benchmarks they tested on AME 2024, AME 2025, AMC 2023, Minerva Math, Emma, TASH 500, the whole works. MRT actually achieved 2 to 3 times better accuracy relative to just using standard reinforcement learning, just focusing on the final answer. They break it all down in Table 1.
Wow, that's a huge jump in accuracy. Just by focusing on the quality of the reasoning steps, they got the models to become much better problem solvers.
Absolutely. And it wasn't just about being more accurate, it was about being more efficient too. In that open-ended setting, MRT needed about 1.5 times fewer tokens compared to GRPO to reach similar accuracy levels. And get this, it was 5 times more token efficient than the base models, just using raw thinking power. They've got a nice chart showing this in Figure 7. And similar story in the backtracking setting, 1.6 to 1.7 times better token efficiency than GRPO, and another method called RISE, shown in Figure 8.
So not only are these models getting smarter with MRT, they're also getting leaner, doing more with less. That's huge for actually using these models in the real world, right? Makes them less computationally expensive, easier to scale up.
For sure. And to really drive home how well MRT was working, they looked at that cumulative regret metric we talked about. In Figure 9, you can see how MRT consistently had lower regret than both the base models and the ones trained with just the final answer reward. And not just within the token limits they trained on, even when they simulated larger budgets, kind of like extrapolating their performance, which they call budget forcing.
So it's like MRT is teaching these models to navigate the problem space more strategically, taking more direct routes to the solution, less wandering around, more purpose in their thinking.
Right. They also had some interesting findings about the length of the reasoning process. They saw that MRT could actually sometimes shorten the average reasoning length while still improving accuracy. This is different from just penalizing longer outputs, which often backfires and hurts performance. Table 1 and Figure 10 lay it all out. The key takeaway is that it's not about thinking longer, it's about thinking smarter at each step, making real progress. Figures 11 and 12, looking at the deep scale R model, really show how important this is. Maximizing progress is key, even more than just giving the model more tokens to play with.
Love that. It's not a brute force approach. It's about elegance, finding the most efficient path to the solution.
Exactly. And they also looked at something called the mange at p metric. Basically, this looks at how the model's predicted answer changes as it generates more and more reasoning steps, those episodes. By tracking the accuracy of the majority vote over these intermediate predictions, they could see if adding more thinking actually led to more reliable answers. Figures 3 and 7 visualize this. And it turns out, standard RL, just focusing on the final answer, it doesn't always guarantee that adding more steps actually leads to better results.
Interesting. So just letting the model think more doesn't automatically make it wiser.
Right. And they even had this case study with the DeepSeek R1 model, which is considered state of the art, shown in Figure 3. Even this advanced model didn't naturally optimize for that record we talked about. Even with lots of tokens, it doesn't always making steady progress in its reasoning.
That's surprising. You'd think the best models would be naturally good at efficient thinking.
You'd think so, right? But it just goes to show that explicitly encouraging progress during reasoning, like MRT does, it can make a real difference. So, looking ahead, what are some of the open questions, the future research directions that this work points to?
Yeah, now that MRT is out there, what are the next steps?
Well, the researchers themselves highlighted some interesting areas. One is the design of that meta-prover policy, the one that estimates the progress in each reasoning episode. They're curious if their current approach, having the model predict the most likely answer based on what it's thought of so far, is the best way to measure progress. Maybe there are even smarter ways to do it.
So refining their tools for measuring progress itself could lead to even better results. Makes sense.
Another big question is what kind of base language models work best with MRT? Are there certain architectures or ways of pre-training that make a model more receptive to this kind of meta-reasoning approach?
Yeah, different models might have different quirks, different strengths and weaknesses that could affect how well they respond to MRT.
And they also mentioned a practical challenge, efficiently implementing these branched rollouts. Ideally, to get a really accurate estimate of the progress reward, you'd want to explore multiple potential next steps from each point in the reasoning, but that can get computationally expensive quickly. So figuring out how to approximate these branched rollouts more efficiently, that's a key area for future research.
It's a trade-off, right, between getting a more precise measurement of progress and how much computing power you have to throw at it.
Exactly. And on a broader level, they're interested in this fundamental trade-off between training effort and test time performance. How much does investing in MRT during training, which can be a bit more computationally demanding, actually pay off in terms of efficiency and accuracy when you're actually using the model? They believe that even with the extra training costs, MRT should ultimately be more efficient overall compared to traditional methods when you look at the total computational resources used across training and testing. But rigorously testing this, that's a crucial area for future research.
Fascinating stuff. Clearly, MRT is a big step forward, but it also opens up all these new avenues for exploration, new questions for the research community to tackle. So for our listeners who've been following along, let's recap. What are the big takeaways about meta reinforcement fine-tuning?
The big picture is MRT offers a much more sophisticated way to train LLMs for these complex reasoning tasks. It's not just about getting the right answer in the end, it's about rewarding the quality of the reasoning process, how efficiently the model gets there. And that leads to some really impressive gains, both in how accurate these models are and how much computational power they need.
Right. It's about guiding the model throughout its thought process, teaching it not just what to think, but how to think effectively. And for you, the listener, what does this mean? Well, MRT is a peek into a future where AI can reason much more powerfully and efficiently, potentially unlocking new capabilities and making these technologies more accessible, less resource intensive.
Exactly. And here's something to ponder, this idea of rewarding progress, not just the final outcome. It's a pretty powerful concept. Goes beyond just AI even. What if we applied this to other complex systems or even our own learning? What if we focused more on those aha moments, the gradual steps of understanding, not just the end goal?
Really makes you think. Maybe focusing on the journey, celebrating the small victories along the way, that's a key to more effective learning and problem solving everywhere, not just in AI. And for those of you who are itching to dive into the technical details, see the math behind all of this, we highly encourage you to check out the research paper itself. It's a great starting point for exploring this whole world of Meta RL and its potential for making AI even smarter. Thanks for joining us for this deep dive.
My pleasure.